Welcome back. I have here on my breadboard an Arduino, this time an Arduino Nano V3, not an Otteri, so blast from the past, and connected to it the star of today's show. That little thingy here, that's an Melexis MLX90363 Triaxis Magnetometer. And today we will go over the basics of that thing. Enjoy! Let's go over the highlights on the first page of the datasheet real quick. So we have a Triaxis, registered trademark magnetometer, meaning we can measure the magnetic strength in 3 axes, Z, X and Y. It has on-chip signal processing, so this is not simply a sensor, it does some processing for you. It has an SPI interface, which is good, so it means nearly every microcontroller can talk to it, self-diagnostic features. 5 volt and 3.3 volt operation. That's also important. That means without any level shifting and stuff, you can use that with almost every microcontroller on the market. 14-bit output resolution, 48-bit ID number. A SOIC 8 package with a single die inside, or a TSOP16 package with 2 fully redundant dies inside for mission critical stuff. I have of course here the SOIC 8 package because if push comes to shove, I can solder a SOIC 8 also with a soldering iron, and I don't need to do reflow work. Applications, and that's how they got me hooked on that thing. So absolute contactless position sensor, whatever that means. I mean, it's a magnetic sensor. Steering wheel position sensor. I'm already using the Allegro A1335 for that application. Card or cards here, many links in the description. And the Allegro A1335 is the superior, much superior chip for that specific application. But then 3D joystick position sensor. What I understand under a 3D joystick is a joystick where you not only can have X and Y axis, but also the rotation of the joystick stick. The joystick stick, is that a word? So really you can input 3 axes, and that's what I'm really interested in, but I fear we will see that in action, if that's not only a marketing gag, in the details video that will follow. Description, more marketing blah blah, but they cannot shut off about their Triaxis Hall technology, stating that conventional planar Hall technology is only sensitive to the flux density applied orthogonally to the IC surface. The Triaxis Hall sensor is also sensitive to the flux density applied parallel to the IC surface. This is obtained through an integrated magnetoconcentrator, IMC, which is deposited on the CMOS die. Before we talk a little bit more about that Triaxis registered trademark technology, let's have a look at the functional diagram at the very bottom of the first page. So we have here our Triaxis sensor that should be simply 3 Hall sensors, and we have a MUX, and we have an analog to digital converter set up, and then we have a DSP with some RAM, EEPROM, wow, a microcontroller, and some ROM firmware, and then we have here an output stage, which is basically your run-of-the-mill SPI interface with MISO, MOSI, slave clock and slave select, a ground, VDD, an internal 3.3 volt regulator. You remember you can run that thing on 5 volt or 3.3 volts, also the digital input-output here. And then that's, I guess, the internal 3.3 volts that you get out on that pin here. Let's talk now about that Triaxis Hall technology with its integrated magnetoconcentrator IMC. Please note, registered trademark, no patents, not even pending ones. I've drawn here a little Hall effect sensor chip, not to scale, mind you, also the proportions are probably wrong. Anyway, here in blue, that's supposed to be a Hall sensor measuring magnetic field lines that go perpendicular to the chip's surface. How these Hall sensors work, I've already explained in detail in the video about Hall switches. Card here, link in the description. The important thing here is to measure those field lines perpendicular to the chip's surface. We need a conductor with a certain area. The larger the area, the more sensitive our sensor will be. It doesn't have to be very thick though. A problem arises when we want to measure not only field lines that are perpendicular to our chip's surface, let's call that the Z-axis and this the Z sensor with the area A times B, but field lines that come from the side, any side. Let's call that direction the X direction, and we have now a second sensor, an X sensor for those field lines. We can make that X sensor as wide as our Z sensor here, so B is the same, but we are very limited in the height we can implement. It's really easy to implement planar structures on a die, but when you want to implement vertical structures on a die, you are really limited in what you can do. And so usually, if we really want to implement all our sensors on a single die, the sensors for the X and the Y axis will be much less sensitive. So, how did Melexis solve that problem with their Triaxis registered trademark technology? Simple. They implemented the X and of course also the Y sensor as planar structures. And well, if field lines come now from here and that X sensor looks on the die exactly as the Z sensor, obviously, it cannot measure those field lines. And here's where the integrated magnetic concentrators come in. My best guess is these are just some blobs made either of mu metal or permalloy. Both these materials kinda attract and concentrate magnetic field lines. Mu metals are usually used to shield stuff from magnetic fields by redirecting magnetic fields around the area you want to shield, while perm alloys are usually used in transformers just to concentrate and direct magnetic field lines. Anyway, with those two IMCs in place here, if we now have a field going in that direction, the field lines are first attracted and concentrated here through the first IMC, and then are directed into the second IMC here through our planar sensor and come out the other side. Wow, that's kind of easy. However, I'm sure my geometry here is completely wrong, and there's probably the secret sauce in getting the geometry of these IMCs right so that you can really direct a part of the magnetic field through your planar sensor. Please note that the field lines here are still at an angle that is, while they are concentrated, each field line will register with less force in the sensor. Another problem I see is that our planar sensor here, of course, also registers field lines going here in the Z direction, at least without any additional shielding. And here's the page where Melexis itself is explaining their Triaxis registered trademark integrated magnetic concentrator Hall technology, which is, I was wrong there the first time, a patented innovative magnetic sensor technology. So there are patents. So what we have here is basically our die, and on that die we have 1, 2, 3, 4 Hall sensors integrated, and then we put a disc-like magnetic concentrator on the top. So in the Z-axis, that thing concentrates the field lines and sends them for the Z-axis through all 4 sensors. Okay? Now in the Y direction here, yeah, they use a little bit different Y direction than I do, but nevertheless, in the Y direction here, the field lines are also concentrated, but only in these 2 sensors here, while in the X direction, logically, the field lines are concentrated in these 2 sensors here. Yeah, the 4th one is completely blocked here by the concentrator. And without some digital signal processing, you cannot get pure X, Y, Z signals out of that setup, okay? It's a nice way to do this all planar on a chip, but you need some post-processing to get valid measurement data for your Y, X, and Z axis. Yeah. In that respect, that far too small functional diagram on page 1 can be easily misinterpreted, because we have here our Triaxis sensor setup, and then we have here explicitly stated 3 signals going into our multiplexer before the analog to digital conversion, and that's VX, VY, and VZ, and that's, I guess, not really the case. You get here 4 signals from your 4 Hall sensors, and that goes into your MUX, and that goes into the ADC, and then the DSP is figuring out what's the X, Y, and Z component. Before we see that little guy in action, let's have a quick squiz on what I have here on the breadboard. And I followed one-to-one the recommended application diagrams for 5 volts here. So if that's a little Arduino Nano V3, the 5 volt line goes to the VDD pin, and we have a little decoupling capacitor here, 100 nanofarad connected to the ground line. The ground line goes also, of course, to the VSS pin. And then we have a smaller decoupling capacitor here going to the VDEC pin. That's the output of the internal 3.3 volt regulator. And the digital lines, so MOSI, slave select, MISO, and S-clock, work all on 5 volts in that setup, and they go to my Arduino D13 S-clock, D11 MOSI, D12 MISO, and I use D10 for the slave select. If you want to use that thing in 3.3 volt mode, it's quite simple. Our 3.3 volt VCC, or VDD like they call it, goes to VDD and to the VDEC, so the 3.3 volt pin, basically completely bypassing the internal 3.3 volt regulator. And we only need one 100 nanofarad decoupling capacitor to ground here. Everything else is the same, and then our IOs will also work with 3.3 volts. I forgot to mention there is a test pin, and for normal operation that has to be connected to ground. Enough with the theory. Let's have a look at some existing Arduino code. hope it's Arduino code, for the MLX90363. There's not much out there. I found two GitHub repositories. One from Otteri called the MLX90363 Rotary Program, and another one from Popos123, simply called MLX90363. Links to both repositories in the description. Now let's jump over to the Arduino IDE and have a closer look at what that thing does. And it doesn't do too much, does it? Let's stop the auto scroll. Here's my chip without any magnet at the moment. So we get here an angle, only the least significant bit or byte, then the whole thing in degrees, and that's wildly fluctuating. And we get error bits. One is obviously set, which makes sense because there's no magnet. A CRC in decimal, virtual gain, whatever that is. We will have a look at that in the details videos, and the rolling counter. Anyway, let's go into autoscroll again and use a magnet on that thing and see if something happens. So the error bit is now -1. That's interesting. And if I turn here slowly, yeah, the angle reading is slowly but surely changing. I mean, this is not a precision setup here, but yeah, it's reading the angle of rotation. Very nice. So at least I know that my little breadboard setup is working. But yeah, that's not really interesting. Let's skip over the code real quick. So we have here the header. We read that already in the repository. We're including standard I/O and SPI, of course. And then we define our pins. Please note, I think I changed the slave select pin here so it fits my setup. Then we have two SPI buffers, 8 bytes each, one for read and one for write. Then we have a lot of buffer variables here to store the process data. So the angle in degrees, angle least significant byte, error least significant byte, the roll counter as decimal, virtual gain, and the CRC, whatever that is good for. And I know what it's good for, but I don't see the code doing anything with it. Then we create a conversion factor for our 14-bit, so I guess that's stored in 2 bytes, angle data to convert that from binary into a float. We have here our SPI settings, so 500,000 MSB first and SPI mode 1. That's always good to know. I'm sure in the details video we find that in the documentation. We set our pin modes for all pins, not only the slave select pin. We deselect our slave by pulling the slave select pin high. We begin our serial communication and we do an SPI begin. And we are in the loop where we first issue a get1 message, binary encoded into the SPI write buffer, which is interesting, but you can do that. And I mean, he wrote, it's just a code snippet, okay? Then we do an SPI begin transaction with our SPI settings. We pull our slave select pin low, so our slave is now listening, and then we transfer the write buffer via SPI, all 8 bytes, to our chip, and we receive 8 bytes, as it is usual with SPI. We pull our slave select high, deselect the slave, wait a second, and we end that transaction. Obviously, we do at that point nothing with the 8-byte we received, which also makes sense because we just issued an SPI command, quite lengthy one, 8 bytes to the chip. So next we write a NOP message in our write buffer, so no operation. And this is exactly the same as before, but now we are receiving in the read buffer the 8 bytes as a reply of our first get1 message, which we sent over SPI. So this is always a two-phase affair. Yeah, and then we do some calculations. I'm just skipping over it. We will see there more about that in the details. And we print out the result. We've also seen that. And we are using sprintf to format stuff nicely. That's it. Here's what the other code does out of the box. Yeah, well, it gives us the angle, least significant byte. It's 2 bytes. I don't know what they're talking about. Anyway, let's put a magnet here and we see the numbers are changing when I rotate here. That's good. We went over 360. Let's go back here towards 0 and, oh, minus. We can get a negative value. No, that's an error value, I guess. Okay, so I can measure the rotation of my magnet. Great. Let's have a short squint at that code too and maybe modify it. It seems to be more code, so it should be able to do more. The sketch from the library that comes as an example is really minimalistic, so we're including here Arduino.h, I'm not sure why. And we include that MLX90363.h file, which we will also have a look at. That's the library, there's no CPP file. We create an object magnet of the class that is probably defined in here, I'm going by the name. Then we do a begin with that object, no parameters here for the constructor, and that gets the MOSI, MISO, S-clock and chip select pins. I changed the pins to fit my setup again. You can also do that for a blue pill. And we do a serial begin, and then we are already in the loop. We issue a read data method of the class, and we print out again that angel LSB, and then we do a delay of 1 second. The .h file starts with some if-def stuff, so if you define software, it will use software SPI, otherwise the hardware SPI library. And we define a class magnet with some private members, either a pointer to a software SPI or a hardware SPI object. And yeah, the rest is the same, like the little bit more unstructured script we saw before. We have a SPI read and write buffer, 8 bytes again, all that temporary variables, the conversion factor from the 14-bit binary value to degrees. And now we have here a public void begin. Yeah, nothing new here. Either software SPI or hardware SPI. And then we have a read data. What does that do? A delay of 100 microseconds for the STM32. You won't need that probably for an Arduino. And we put a get1 message into our write buffer, and then we do begin transaction. And we select our chip with the chip select pin, and then we write out the 8 bytes to the SPI bus. We also receive 8 bytes, but we don't really use them. Then we deselect our chip, and then we wait 800 microseconds. And then we fill our write buffer again with a knob message. So nothing really new here. Do either software or hardware SPI. We transfer again those 8 bytes with the knob, and we receive in the receive buffer the result from our first get one. Deselect and end transaction. And then we have here Angel LSB method, which somehow extracts from our 8-byte read buffer the LSB bytes. More interestingly, angle in decimal, and we saw that before. The arrow bits that are also somewhere hidden in the buffer, and the CRC, which is somewhere hidden in the buffer. The virtual gain that it's included in the buffer, and the rolling counter that's included also somewhere in the buffer. And that's it. Just as to really see something, let's use in the code in our sketch not the angle LSB, but where was it? The angle in decimal. So I just changed here in the sketch the serial print, and I'm printing here now out the angle in decimal. Let's have a look at the serial plotter this time. Off camera, I also changed the delay from a second to 100 milliseconds, so we have at least a chance to see something here. So, okay, now we got a signal, and now I'm rotating my magnet. Sorry, fingers in the way. Rotating, rotating, rotating. And yeah, that's it. We're measuring the rotation of our magnet. Okay, that's not a very good setup to do that, but yeah. Here it is. I don't know why we get those high values in between these peaks. This is obviously an error value. I would have handled that differently, but anyway, yeah. So both examples just measure the angle. Yeah. And here's the promised explanation about the magnet I'm using. That's a diametric magnet. That is, if you cut it, seen from here, into half, one half, the blue one, is the North Pole, and the other half, the red one, is the South Pole. That's a little bit unusual because normally such small neodymium magnets have one pole at the top and the other pole at the bottom. A detailed explanation about that and how they work with magnetic angle sensors you can find in the first basics video about the Allegro A1334 card here, link in the description. But that chip is supposed to be able to do so much more than we have seen in these more code snippets I found. So it should be able to do linear motion measurements with magnets, rotary motion, we saw that, and also joystick motion. So I guess that's what they call 3D. I call that yeah, it's kind of 3D. So, and you can do on-axis measurements, as I also done with the Allegro A1335. Off-axis measurements, you can do that also with Allegro A1335, also with Allegro 1334. And then that joystick stuff here, that is very interesting. And again, yeah, kind of linear stuff, but also with a diametric magnet up and down. Very interesting. So we have a lot to look forward to in the details videos that will definitely follow. That's it for today. That was a quite short and not very satisfying the basics videos, because there is not much code out there that is really exploring all the possibilities of that little chip, so I couldn't show you much. Nevertheless, we will continue with the details, which will be probably a quite long series of videos where we write our own library and really try to max out on what that thing can do. Till then, bye!